Okay, folks, as you can see, I am dressed in my Sunday best, but I'm going to do a little bit of a video on deriving our centripetal force equations. So, diving in, here we go. Our old buddy, F is equal to ma, FMA. Now, our new equation for centripetal acceleration is v squared over r. Substitute that in. So you get F is equal to m v squared over r, or our new equation. It's just another version of Newton's second law of motion, which is F is equal to ma. It's just nifty and cool looking now because we can use it now for different things, particularly things going in circles. So when we're talking about circles, centripetal acceleration, centripetal motion, we have a force, which we call centripetal. Don't say centrifugal or centrifugal. You sound stupid. Okay? This is the only force there is in a circle. Centripetal, center-seeking force. Okay, now what I want to do this week is go over some applications using this in different situations. But before we can do that, I want to show you something nifty and cool. If we look at our old buddy, this is the universal gravitational constant equation. So G m1 m2 over r squared. Okay. If we look at that, we know that if we remember, I kind of was showing you at one point that you can use this to figure out the force of weight of an object. And you might say, well, why would you do that? Because we have another equation, Fw equals mg. And it's just so much easier. True, it is easier. And this is what we would use if we're on the Earth near the surface. This one we could use there as well, but you can use this anywhere, it's universal. What I want to do is make a substitution in. Let's substitute in Fw for Fg, because it is the same thing. So if we do that, then our Fg equation now looks like that. And that m here cancels out with the m over on the right. So I end up with this equation. Little g equals big G m divided by r squared. Now you might be saying to yourself, why'd you show me that? Well, here's why. Because if you have something going in a circle around the Earth, that, people, is called a satellite. Horses like satellites. They don't like saddle heavies. Joke. It's funny. Think about it. All right, so now what I'm going to do is erase this, because this was really last week's material, but just wanted to go over it quickly again with you. And now let's say to ourselves, let's keep this equation in mind and look and see what it is a satellite is. Well, a satellite is anything that goes around something else. The Earth, of course, has satellites. So if you're the Earth, you have a satellite that's there without any people. That's called the moon. That's a satellite, people. That's a natural satellite of the Earth. We also have man-made satellites that orbit the Earth. So if we have a satellite out here at this level, and maybe that's the moon, okay, maybe whatever. It's a satellite, we'll call it the moon. And it's circling the Earth. Well, here's the thing. G here isn't G here. So G here is going to be a lot less than G here. Farther away you get from the center of the Earth, the less G is. So this is going to be different than this. Oh, that's why we need this nifty, cool equation in order to calculate what G is. It's some distance away from the center of the Earth. So G for satellites around the Earth can be calculated at some height above the Earth if we use this nifty cool equation. And we're going to need that. So the mass of the Earth, the distance from the center of the Earth. So if we put the moon here, that R value that goes in here, the distance from the center of the Earth, is this distance right here. Not from the surface of the Earth, from the center of the Earth. So what we have to know then is what is the radius of the Earth, because we'll have to add that to the distance above the Earth that the satellite is. Also, we need to know the mass of the Earth. Now, the mass of the Earth was calculated. You can get the mass of the Earth by three ways. One, you could get a really big balance, find one sticking underneath the Earth at Antarctica and see what it says. Second thing is you can fly down to Antarctica, just fly right in, South Pole, and ask Atlas. He's holding it up. Third way is you can calculate it. Using this equation, you can calculate the mass of the Earth if you know universal gravitational constant, if you know the radius of the Earth. The Greeks know that thousands of years ago. They were smart people. And you know little g, which we can calculate relatively easily, just drop things time in. So yeah, it's a calculated value. So this mass of the Earth comes out to be 5.97 times 10 to the 24th kilograms. I'm running out of room there. It's looking kind of small, but we'll write that. So let's see, mass of the Earth, 5.97 times 10 to the 24th kilograms. Okay, armed with this information, we are ready to do a satellite problem. Now, I'm going to erase this for now. We'll come back to this satellite problem. You were assigned a video to watch, and that video to watch was on Bugs Bunny throwing a baseball around the world. Don't doubt it, it's Bugs Bunny, he can do it, okay? End of story. And we know the Earth is round because it came back with the different stickers on it, London, Paris, Tokyo. So clearly around the Earth. Okay, so we know that the Earth is round because of Bugs Bunny. Second thing is, I want to figure out how fast did Bugs Bunny have to actually throw that baseball? How fast did he have to throw that baseball in order to put it in orbit around the Earth at the surface of the Earth, or near the surface of the Earth, he's a meter above the Earth. So how do I figure that out? All right, so I need an equation that's going to help me figure this out. Let's see, let's go back now to my centripetal force equation. There are different causes of centripetal force. If you're a cowboy / cowgirl, the lasso, you're going, woo, yippee-ki-yay. Okay, you are the source of the centripetal force, twirling that rope around. If you're a car going down the road and you're taking a turn, the thing that keeps you going in a circle is the friction between your tires and the road. That's a different source. Also, if you are a satellite, what's keeping you going in a circle? Gravity. It's gravity. Without gravity, the satellite goes, bye-bye, see ya, wouldn't want to be ya. So it takes off. So we know that gravity is the source of centripetal force for a satellite. Therefore, the satellite's own weight, the gravity pulling on it, its own weight, is equal to the centripetal force. So for a satellite, mg, weight of a satellite, is equal to the centripetal force, which is equal to mv squared over r. You can see it. Yes, you can. You know what's going to happen. The mass of the satellite cancels. It doesn't make any difference what the mass of the satellite is. It's irrelevant, the mass of the satellite. If you want to put a satellite in orbit, it doesn't matter what the mass of the satellite is. What you need to know is how far from the center of the Earth you're putting it. That's r. So therefore, you can get it going at a certain velocity given the gravitational pull at that height. So I don't need to know the mass of the satellite. Doesn't matter. You can have a truck or a marker at 10,000 kilometers above the surface of the Earth, and they would both have to travel at the same velocity because the mass of them doesn't make a difference. So this now can be moved and converted, moved around. So we'll move this. Just want to keep in the screen here. So let's move this and solve for v. So v is equal to the square root of g times r. V is the square root of g times r. That is my velocity of a satellite equation. It's very simple. It's not a hard equation. Let me move that back in here so we'll get it in the better range of the screen. So the velocity of a satellite is equal to the square root of g times r. Easy. Piece of cake. Now, how fast was Bugs Bunny throwing the baseball? We can do that. The velocity of the baseball, the satellite, is equal to the square root of g. Now, he's at the surface of the Earth, so little g is 9.8. 9.8. Multiplied by the radius of, or well, actually in this case it'll be the radius of the Earth, but the reason is because Bugs Bunny is at the surface of the Earth, so the distance from the center is the radius. We need to know the radius of the Earth. Well, we all know that the Earth has a radius on average, because it does vary between the poles and the equator. The equator is a little bit wider. It's like a piece of pizza spinning around, you know, a pizza dough, it eventually gets wider. So the Earth is a little bit wider at the equator, but on average, it's 6,370,000 meters. So that's 3,670,000 meters. That's a lot of meters. After that many meters, even I could get a date. Meet her. Even I could get a date after that many. Okay, never mind. Do the math. Calculate it. Multiply that by 9.8, which has been essentially 10, so it's like 63,700,000. And don't forget to take square root of it, because it can be really fast otherwise. Take a square root, and you should come out with a value that is about, I'll write it up here, 6,730 meters per second. Pretty fast. But let me just check that, because I'm just doing that off the top of my head from memory here. Could be incorrect. It happens once in a while. I remember 1986, I was wrong. That was because I thought that the Red Sox were going to win the World Series in Game 6. Nope. I was wrong. Hang on. Okay. Answer. Oh, dang it, I was wrong. You know, you can never trust a guy wearing a sweatshirt. Ties, yes. Sweatshirt, no. It came out to be 7,901 meters per second. And that 1 meter per second is important. Don't forget it. You might say to yourself, that's just where my brain was. My brain's been a mess lately, okay? So that's, yeah, okay. That's the answer. Bugs Bunny, you kick butt. That comes out to be about 18,000 miles per hour, 18,000 miles per hour, people. And I know you're saying to yourself, Sal, that's not realistic. Bugs Bunny couldn't do that. Yes, he could. He's Bugs Bunny. He could do it. He could throw it 18,000 miles per hour. Don't be doubting the bugs. All right, now, here's the thing. Bugs was throwing that at the surface of the Earth. What would have to be the velocity that Bugs Bunny would throw the baseball if he had to throw it, 10,000 kilometers above the surface of the Earth? So here's our Earth. That's R. We want to take and throw this baseball, or put it in orbit. We guess we could throw it. If you're Bugs Bunny, you could, just to get up there. You want to throw it around the Earth and keep it in orbit at 10,000 kilometers above the surface. Well, I know what you're saying. You're relatively intelligent people. You're saying to yourself, G ain't going to be 9.8 up there. That is correct. That is correct. That's the problem. All right, not a big problem. We can now handle this. What we're going to have to do is add together these two values to get the height above the Earth that we're launching the satellite, keeping the satellite in orbit. Okay, let's see. That's going to be, so R, or the distance above the center, will be 637,000 meters. That's 6,370 kilometers. Plus 10,000,000, because we got to make sure that's in meters, not kilometers. So altogether, that's going to be, excuse me, 16 million 370,000 meters above the surface of the Earth. Great. All right, here we go. Let's see. Let me go back to that equation for a satellite. How fast the satellite will have to be going is G times little r. Ruh-roh, Rastro. G ain't 9.8. Oh, how are we we can't do this, I quit. I'm not gonna do it, I quit. No, remember earlier we derived the equation to solve for G at that height. So we could either do one of two things. We could solve for G by using that equation, or we could substitute that equation in for G and get an overall satellite equation that'll work for any satellite, any satellite, any satellite at any height, any height, any height. So I'm going to do. If I do the substitution, little g, as we solved earlier, is equal to big G times the mass of the Earth over r squared. Okay, let's get this out of the way. Okay, times r. Yeah, that was my little g calculation I came out with earlier in the video. Cancel. Cancel, cancel, cancel. Boom. This equation for a satellite, some people like it better than the other one because, I mean, some people like this one because it's small, it's easy to remember. I'll just calculate little g, plug it in, solve it. Fine, great, awesome. I like this one because it's get it all over with all at once. Let's do it. Do the math. Velocity equals big G, and we all remember big G. 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the 24th. A lot of big numbers here. A lot of big numbers. This is a big number too, remember. This is 16,370,000. And don't square it. We got rid of that r, so don't square that. But we do have to take the square root of this whole thing when we're done. Okay, let's do it. Let's do it. My nose is itching. My nose is itching. What does that mean? If your ears ring, somebody's talking about you. I don't know what it means if your nose itches. All right, here we go. 6.67, second function exponent, negative 11, multiplied by 5.97, second function exponent, 24, equals. Okay. Now, we're going to take 16,370,000 and divide that into that number. Oh, no, driving me nuts. All right. 3. No. Thank you. Okay, so that's the 3.98. Okay. 16. There it goes. Oh, square root, don't forget to square root. 4,930, 4,930, which sounds right, 4,930, 4,930, 4,930 meters per second. Makes sense. It's slower than Bugs Bunny had to throw it. Bugs Bunny had to throw that ball 7,901 meters per second. We're farther away from the Earth. Less gravity. Less gravity, it doesn't have to move as fast. In fact, if you was moving at 7,901 meters per second at 10,000 kilometers above the Earth, it would take off. Gone. See ya. In fact, that's what I'm going to say right now. See ya.